Okay, I'm going through a homework I set recently on mole exam questions. So it's important to note that questions 1 and 2 could appear on both the foundation and higher tier paper. Questions 3 and 4 are higher tier content only. So question 1, magnesium reacts with steam to produce hydrogen gas and magnesium oxide. A teacher demonstrated the reaction to a class. The figure below shows the apparatus the teacher used. So part A asks that hydrogen produced was collected. Describe the test to show it's hydrogen. So this is a squeaky pop test. So you need to say that you hold a lit splint to the gas, or you ignite the gas and it makes a pop or a little explosion. A lot of people will just say squeaky pop test, but they want the method, holding a lit splint, and they want the result, the squeaky pop. Part 2 then, explain why the magnesium has to be heated to start the reaction. So this is linking to energy profiles. We need to provide enough energy to get the reaction started, and that energy breaks those bonds. So 1 mark for saying it provides energy, and the second mark is to break bonds. 1b, the equation for the reaction is magnesium plus water makes magnesium oxide plus hydrogen. The teacher used 1 gram of magnesium. Use the equation to calculate the maximum mass of magnesium oxide produced. Give your answer to 3 significant figures. That's going to be important later on. So, first question we can ask ourselves is how many moles of magnesium do we have? Because we know the mass and we know the AR. So, moles of magnesium is going to be the mass divided by the MR, so 1 divided by 24, and that gives us 0.0417 moles. Now we can see from this equation, which is balanced, that there's a 1-to-1 ratio throughout. So 1 mole of magnesium will react with 1 mole of water to form 1 mole of magnesium oxide and 1 mole of hydrogen. So, because that 1-to-1 ratio, we know there must be 0.0417 moles of magnesium oxide. So we now know for magnesium oxide the moles, and we can work out the MR. So moles times MR gives us a mass, that's 0.0417 times 40 to give us an answer of 1.67 to 3 significant figures. Part 2 then, the teacher demonstration produced 1.5 grams of magnesium oxide. Use your answer from part B to calculate the percentage yield. If you could not provide an answer, use 1.82 as the maximum mass of magnesium oxide. This is not the answer to part B.1. So we've worked out part 1's answer. We said it should be 1.67. Now your percentage yield is what you've got over what you should have got, so your actual yield over your theoretical yield. So the teacher got 1.5. We know they should have got 1.67. Divide those numbers times by 100, we get 89.8%. They would have accepted you rounding up to 90% in this question. We're then asked, why didn't we get 100% yield? So there were lots of reasons you could have given this. Most common answers were not all the magnesium reacted, or some magnesium oxide was left in the tube, or maybe lost when you transfer it to the scales. Question 2. An experiment was done on the reaction between copper oxide and methane. The equation for this reaction is shown below. So we have 4 lots of copper oxide, and we've got an SF solid plus the methane gas forms copper solid, water as a gas, plus carbon dioxide also as a gas. The water and carbon dioxide produced escape from the test tube. Use the information from the equation to explain why. So they wanted you to use the state symbols I've just highlighted here. So they tell you that both those compounds are gases, and so they can escape. Then asked to calculate the relative formula mass of copper oxide. They've kindly given you the numbers from the periodic table, so we just need to add them together. 64 plus 16 equals 80. So asked to calculate the percentage of copper in copper oxide. We know the MR of the copper oxide, and we know the MR of copper. We've given that, so let's put them together. The percentage of copper is going to be MR of copper divided by the MR of copper oxide, and we times it by 100. So that gives us 80%. We're then asked to calculate the mass of copper that can be made from 4 grams of copper oxide. Well, 80% of copper oxide is copper, we just need to work out 80% of 4 grams, and that gives us 3.2 grams as our answer. We're told the experiment was done 3 times. The mass of copper oxide used and the mass of copper made was measured each time, and the results are shown in the table. Calculate the mean mass of copper made in these experiments. So looking at our results, they're pretty close. There's only 1 mark going here. There's not any anomalies, so I'm just going to add up those 3 numbers for the mass of copper and divide by 3. And that gives an answer of 3.33 to 3 significant figures. We're then asked to suggest how the results of these experiments can be made more precise. So that's when we're looking at our decimal places, maybe using more sensitive balance, so one that measures with more decimal places, or apparatus. Part 3, the 3 experiments gave slightly different results for the mass of copper made. This was caused by an experimental error. Suggest 2 causes of experimental errors. There were loads of suggestions here, so I've just put them all down for you on the screen. But they're not after systematic or human errors. We're looking at maybe using different balances, or maybe the balance was faulty. Maybe there was an incorrect reading, maybe you spilt some of the sample while you're doing the experiment, maybe there was impurities in the sample, maybe you heated for different times or heated at different temperatures. The list goes on. Question 3 then is about acid and alkalis. Dilute hydrochloric acid is a strong acid. Explain why an acid can be both described as strong and dilute. So you probably spent a lot of time in class looking at the difference between strong and weak acid and dilute and concentrated. If an acid is strong, it means it fully deionizes, so all the hydrogen is liberated from the compound it's in and can be measured in solution. That's what we record with pH, that measurement of hydrogen ions. If it's dilute, it refers to how much acid there is in a given volume. So if you think about squash, you dilute that. If it's concentrated, there are lots of squash compound there. If it's dilute, there's less. So hydrochloric acid can be both a strong acid, which happens to be dilute because it fully deionizes and there is not as much acid in it in a given volume. So a 1.0 times 10 to the minus 3 moles per dm cube solution of hydrochloric acid has a pH of 3. And this number here is important, this link between these two. What is the pH of a 1.0 times 10 to the minus 5 moles per dm cube solution of hydrochloric acid? It's going to be 5. So this titration calculation threw quite a lot of you, so I'm going to show 2 different methods of approaching it. They are doing the same calculations, it's just laid out differently, but people have their natural preference. So a student titrated 25 centimetre cube portions of dilute sulfuric acid with a 0.105 mole per dm cube sodium hydroxide solution. The table below shows the student's results. So they've had 5 goes at the titration, and we've got different volumes of sodium hydroxide there. The equation for the reaction is 2 moles of sodium hydroxide will react with 1 mole sulfuric acid to make 1 mole sodium sulfate plus 2 moles of water. Calculate the concentration of the sulfuric acid. That's what we're trying to work out ultimately. Use only the student's concordant results. And they've been quite helpful here. They've told you concordant results are those within 0.1 centimetre cube of each other. So if we look at our results, we've just got 3 concordant results there. So for our mean volume of sodium hydroxide, we're going to use those 3 values, and we get a mean of 22.13. Now you have to remember in all mole calculations, our volumes need to be in decimetre cubed, so I'm going to divide that number by 1,000 so that I've got a mean volume of sodium hydroxide as 0.02213 decimetre cubed. So those of you who are in my class know that I prefer the table method when doing titration calculations or multi-step complicated mole calculations. which you see more of at A level, but this is kind of your first introduction at GCSE. So why I like this method is I have the equation out, I can work out the molar ratios, which I've already written down, you can see 2 to 1 to 1 to 2, but I also plonk down the information I'm given in the question or I've worked out initially. So I've worked out the volume of sodium hydroxide on average, and I've put it in decimeter cubed, so I've got that information. I also have from the question the volume of sulfuric acid, and I was also told the concentration of sodium hydroxide in the question. Fantastic, so I can see what information I know. I'm trying to work out that light yellow box, the concentration of sulfuric acid. And if I look at my triangle, I don't have enough information. I only know the volume, I don't know the moles to be able to work out concentration. But if I look at the sodium hydroxide, I've got two parts of that triangle. I've got the volume and the concentration, so I can work out the moles. And moles are going to be concentration times volume. So I take those two numbers times together, and I have an answer of 0.00232 moles of sodium hydroxide. Now, going back to my original equation, I know that if I had 2 moles of sodium hydroxide, it would react with 1 mole of sulfuric acid. So if I had 4 moles of sodium hydroxide, I know that it will react with 2 moles of sulfuric acid. They react in a 2 to 1 ratio. So to work out the moles of sulfuric acid, I'm going to divide my answer by 2, and that gives me a mole value for sulfuric acid of 0.00116. Now, going back to my triangle, I now have a volume and a mole, so I can work out concentration, which is going to be the mole value 0.00116 divided by 0.025, and that gets me an answer of 0.0464 moles per decimeter cubed. And you have completed the question. Now, not everyone likes the table method, but it's a similar thought process. You can just lay it out differently. So it's always good to look at your question, maybe use a highlighter to say, what do I know? So we know the volume of sodium hydroxide, we know the concentration of it, and we know the volume of sulfuric acid. So first step, I'm going to find out the moles of sodium hydroxide. So times the volume by the concentration. Then I'm going to find out the moles of sulfuric acid. Now I explained the reason, it's a 2 to 1 ratio, so I can halve the moles of sodium hydroxide to work out the moles of sulfuric acid. And then I can work out my concentration of sulfuric acid because I have the mole and the volume. And voila! Right, question 3 is not finished. We've got part D now. Explain why a student used a pipette to measure dilute sulfuric acid and a burette to measure the sodium hydroxide solution. So pipettes measure fixed volumes accurately. So they only measure, if you remember from using the glassware in class, 1 volume, and you've got to get your fluid in the bottom of the meniscus on that line exactly. Burettes measure variable volumes. We have that control with the tap there. Now for part E, we're asked to calculate the mass of sodium hydroxide in 30 centimetre cubed of 0.105 mole per decimeter cubed solution. So we need to work out the moles of sodium hydroxide first. That's going to be volume times concentration. Remembering to put our volumes into decimeter cubed, I get a value of 0.00315. And then mass is moles times MR, so 0.00315 times 40 gives me an answer of 0.126 grams. Question 4, we're changing topic here. Printed circuit boards are made when copper sheets are etched using iron-free chloride solution. Where the copper has been etched, only plastic remains. Copper is a good conductor of electricity. Explain why. So you're using your C2 knowledge here. And basically, copper has delocalized electrons which can move, which can flow through the structure or through the metal. Part B, iron-free chloride can be produced by the reaction shown in the equation. So 2 moles of iron will react with 3 moles of chlorine to form 2 moles of iron chloride. Calculate the maximum mass of iron-free chloride that can be produced from 11.2 grams of iron. And we're also given the relative atomic masses there. So step 1 is working out how many moles of iron do we have. So moles is mass divided by mR, and I get the moles of iron is 0.2. So I now can use that information to work out how many moles I have of iron chloride, and I can see from the equation that they have the same ratio. There's 2 moles of iron there and 2 moles of iron chloride being formed. So they equal each other, and if I've got 0.2 moles of iron, I must have 0.2 moles of iron chloride being produced. So I can work out the mass of the iron chloride by times in the moles by the mR, and I get an answer of 32.5 grams. I'm then asked the actual mass of iron chloride produced was 24.3 grams. So not as high as my theoretical value, so I'm asked to calculate the percentage yield. So I'm doing what I got over what I should have got. So 24.3 divided by 32.5, the answer we got from the previous part, times in by 100 to get 74.77%.